Okay, so we keep sidestepping things, right? We sidestep the position dependence, then we sidestep the multi-directional heat transfer, and we said, well, let's look at just single direction heat transfer. Well, what about when we have multiple directions of heat transfer? Then what? What if we have a cylinder where instead of it being a long cylinder and the temperature is just a function of how far out from the center we are and how much time has elapsed? What about if we have a short cylinder? And so now there's heat transfer out the ends of that cylinder, or axially. This is called a short cylinder problem. So there is heat transfer in the radial direction and in the axial direction. Well, we finally get a payoff. Things simplify. You see, if you think about it, you can make this short cylinder shape from intersecting a plane wall with a long cylinder. Now be careful, some of the models can't be intersected this way and get anything that's valid. Okay, I'll show you a table in a second that tells you which are valid and which are not. But this is one that can. So if we intersect the plane wall and the long cylinder, then the plane wall can model the axial heat transfer while the long cylinder models the radial heat transfer. It turns out we can do this with two plane walls. We can put them together and say, well, what if we have a square rod where there's heat transfer out of all the surfaces? Now, not along the length of the rod, but out the side of all the surfaces. Well, then all we need to do is intersect two models, two plane walls. Well, how do we intersect them mathematically? What do you do? Well, now, of course, the temperature, let's go back to the short cylinder. The temperature will be a function of what X position you want along the length of the cylinder and what R position you want radially from the center line out to the outside surface of the cylinder, and of course time. So this is really multi-directional. It's two-dimensional heat transfer. In that case, we finally get a payoff. The dimensionless temperature of the short cylinder as a function of radius R and position X axially is simply the product of the dimensionless temperatures from the solution for the infinite cylinder and the solution of the plane wall. And finally, yeah, I know it's a little bit of a pain to get those two solutions, but if you get the two and you multiply them together, you've got the solution for the short cylinder. And so it looks like this if we were to expand these dimensionless temperatures so you could really see them. The temperature we want as a function of two positions, radial and axial, Rx, and T, time, is equal to the dimensionless temperature as a function of just axial position in time and radial position in time. And this is really nice for us. What about for intersecting two walls? So having a square rod, I guess you could call it. Well, in that case, we're interested in the temperature as a function of position toward the upper and lower wall, and position toward the left and right wall, and time. In other words, x1 and x2. In that case, we just need a model to model the heat transfer going out, that's one wall, and another model to model the heat transfer going up and down, that's the other one. Okay, so we just multiply those two together, and now we've got the dimensionless temperature as a function of both coordinate directions and time. And expanding it, this is what it looks like, where again one plane wall takes into account our position vertically and the other one takes into account our position horizontally. Now what about the accomplished temperature change, or the accomplished heat transfer? Well, in that case it's a little more complicated. We need the Q over Q max from one model and the Q over Q max from the other model, but it won't matter which one you define as 1 and the other one as 2. You'll get the same result, but you see the equation here for it. You add to 1 the product of the second and 1 minus the first. Okay, so that's what you do, and remembering what Q max means might be helpful at this point. What about 3D heat transfer? Well, then all we need to do is intersect multiple bodies, and so there are very few models like this that we've got, but the Q over Q max becomes really complicated, and don't worry about this too much. If you care about it, there it is. Let's go on and look at the combinations we can actually use. And there are a couple. I think there's one that's 3-direction. Here's a challenge I've got for you. All of these are models of bodies that are trying to take into account multiple directions of heat transfer, potentially. Some of them are not. Some of them are simple. For example, upper left corner, that's just an infinite cylinder, right? That's a single direction heat transfer. But if you go to the right, one model with a cylinder, then what they're doing is they're intersecting the long cylinder model and a semi-infinite body. Now understand, a semi-infinite body is basically just cutting off that lower surface so that it can take into account axial heat transfer from just that end. Now you might look at this and say, yeah, but there's no semi-infinite cylinder. Well, think about it this way. What if you have a cylinder where one end is insulated? So there's no heat transfer there at that end. Well, that's exactly this model. There's only heat transfer radially and from one end of the cylinder, right where it's cut off, and there's fluid around it transferring heat with it. What about the case where it's a short cylinder? Well, we already saw that if we intersect a wall with a cylinder, then we've got this model, right? We've got a short cylinder that does not have insulation on one side. My challenge to you as we go through is to consider what would the directions of heat transfer be that we are trying to model here. And I usually have this as a class exercise, so we'll probably get together and share answers to this. So I want you to take some time, get a piece of paper and a pencil, and try to figure out what the directions of heat transfer would be for all of these cases. Okay, so the way you can come up with it is pretty simply. Start with the first model, the one that you know. The infinite cylinder only has heat transfer in the radial direction. So you know that the other two cylinders are going to certainly have radial heat transfer. But then look and see what the next body is, the semi-infinite body. See how it's oriented relative to what we've already got. And the semi-infinite is oriented this way because there's the plane face. And you realize that in the semi-infinite body, heat transfer is into the body, right? Normal to the surface. So now you know there's a direction of heat transfer along the x direction. Now be careful with this. It's not just as simple as whatever the coordinate directions are, that's the direction of heat transfer. Maybe, maybe not. Okay. So what about the short cylinder? Well, again, because of the cylinder, we've got radial heat transfer, but because of the wall that's oriented this way, we've got heat transfer out of the top and bottom, either side of the wall. So that's axial heat transfer at either end of that body. Now, on the second row, we've got the semi-infinite medium, and then the second body to the right is two semi-infinite mediums at a right angle to one another. Okay? And then finally, what if we add a third semi-infinite? So imagine we're cutting it off with planes. There's one semi-infinite, and a third semi-infinite body. And then finally, row 3, we've got an infinite plane wall. That's simple. That's a single direction. But what if we have a semi-infinite plate or plane wall? Well, then we've got our wall going this way, and our semi-infinite body has a plane this way where the material goes in, along the length of the wall. Not the thickness of the wall, but the depth of the wall. And of course, we could put another semi-infinite plane and have a corner, essentially, a semi-infinite plate. And you can see the models that get multiplied together so that we come up with a solution for these things. The last row I'll let you think through, but it's basically just combinations of a rectangular bar, an infinite cylinder, or rectangular bars or rectangular walls 3 ways. Okay, so we've got 2 models there at the end that involve 3 different directions of heat transfer.